Here we've got an example of two X versus Y graphs, but at different times. If we want to just know, I mean, ignoring everything else for the moment, if all we want to know is which direction the wave is traveling, then what we want to do is identify not exactly a point in common like we would if we had an X graph and a T graph, but instead, since we've got two X versus Y graphs, they're at different times. One's at time 6 seconds, the other's at time 10 seconds. So there's no way to find a single point on both graphs that have the same coordinates because they've got different time coordinates already. But how far apart are these graphs in time?
4 seconds.
Yeah. So we can treat that as delta t. That these are two snapshots of the wave that are taken 4 seconds apart from each other. And we actually need one more piece of information. Let's say the information is given that the speed here is 2.5 meters per second. If we know the speed and how much time passes, what else can we calculate?
The wavelength.
Well, wavelength would be if we know the speed and the period, which we could measure from the graph. But think back to the original definition of speed. What does speed mean? Yeah, speed is all about distance over time. Distance over time, delta x over delta t. We know the speed. We know how much time passes between these two pictures, these two snapshots. So what should we be able to solve for? If we know speed and how much time passes, what's the only unknown then? Yeah, delta x. In other words, how far the wave travels. Multiplied by delta t, we get distance traveled by the wave during that amount of time is speed times the amount of time. Fill in those numbers. We know the speed is 2.5 meters per second. We know that 4 seconds worth of time passed between these two snapshots. Multiply those, and we get 2.5 times 4 would be 10 meters. So that means over the course of these 4 seconds, the wave travels 10 meters. So what we want to do then on these two snapshots, we want to identify the same type of point on one graph and the other graph that are 10 meters apart from each other. So can you find, is that okay, 10 meters? Can you find the same type of point on both graphs that are separated by exactly 10 meters? Maybe a crest on one of them and a crest on the other that are exactly 10 meters apart, or a trough on one and a trough on the other, as long as they're exactly 10 meters apart from each other. What 2 points would work there?
Are you asking us like the second, for example, the second graph, it would be a crest and a equilibrium point?
Well, we want to find the same type of point. So a crest on one graph and a crest on the other graph that are exactly 10 meters apart from each other. Or a trough on one graph and the same trough on the other graph that are exactly 10 meters apart.
Okay.
So for instance, on this graph, we've got, let's say if we look at the troughs, we've got troughs at 1, 7, and 13. Can you find a trough on the other graph that's exactly 10 meters away from one of those?
The one at 3?
Yeah. If we have a trough at 3 and a trough at 13, those two x values are exactly 10 meters apart from each other. And we know that whichever direction that trough is traveling, it's got to travel 10 meters during those 4 seconds of intervening time. So that means the trough, that one trough is at 13 meters at some time and at 3 meters at another time. But it's the same trough because it's traveling the right amount of distance. So these 2 points represent the same trough as it moves. It's 2 different locations, 13 and 3 meters, and 2 different times, 6 seconds and 10 seconds. But it's the same trough photographed at 2 different locations as it moves. And which one of those happens earlier? Passing the 13-meter mark or passing the 3-meter mark?
The 13 mark.
Yeah, because that happens at time 6 seconds, which is earlier than time 10 seconds. So first, this trough passes the x equals 13 meter location. And then later, the same trough, and we know it's the same trough because it's exactly the right distance apart, 10 meters. Later, the same trough passes the x equals 3 meter location. And specifically 4 seconds later, because we know that in 4 seconds, that trough has to travel 10 meters. We don't know in advance which direction it's traveling, but we now know that if it starts at 13 meters and 4 seconds later reaches 3 meters, which direction has it traveled? Yeah, it has traveled to the left. Because if it starts at x equals 13 and then at a later time, it's now at x equals 3, that means as time passes, this trough's x value has decreased. The trough has moved in the negative x direction, the decreasing x direction. So that means that the whole wave is shifting in the negative x direction, which we would say is to the left. So this whole wave is on its way to the left. Any questions on that? Figuring out the direction of travel.
So, yeah, I just had a quick question. So, just to clarify, we know we don't need to know the wavelength to be able to solve what direction it goes.
Right. As long as you know the amount of time between the 2 graphs, and you also know the speed of the wave, then you can solve for the distance traveled during that amount of time. Or possibly it could be the other way around. Maybe you have 2 time graphs at different positions. As long as you know delta x and the speed, you can solve for delta t and figure out how much time has to pass between the 2 graphs.
Okay. Okay, and we know it's moving left because we're looking at the same point, so we can make the conclusion that because this at a later time it's closer to the x-axis that it's moving to the left.
Yeah, well, not closer to the x-axis, but further in the negative x direction. That at the earlier time it's a larger x value, and at a later time it's a smaller x value. So that means it has moved in the decreasing x direction.
Oh, okay. Okay,
but
cool.
once you've established the same trough on both graphs or the same crest on both graphs, regardless of what type of graphs they are, as long as they're the same type of graph, look for what's the earlier time, or which x value is associated with the earlier time and which x value is associated with the later time. And then you can use that to figure out as time passes, is x increasing or decreasing.
Gotcha. Okay, thank you.
You're welcome. All right, let's try out let's look into the idea of beats as well. Can you see this blank graph all right?
Yes.
Okay. So let's say we have a wave. I'm just going to fill in or visualize this wave here. So this is a wave. Let me see if I can zoom in a bit. Oh, that'll work. So here's a wave with a certain frequency, and the frequency here is 0.65. And if I have another wave, so both of these waves here, and what's the difference between these 2 waves? Actually, let me just stretch this out a little bit. Let's say the frequencies are We'll just double each of those. 1.3 and 1.2. Oh, sorry about that. I think that'll make it work better. Okay, so based on these two graphs, we've got two waves happening. What are the differences between these two waves? Just based on the graph or based on the equations I've got here. Assuming this is a time versus y graph. I've written it as x, but let's treat this as time. If we've got a time versus y graph of two different waves, what do you notice is different about these two waves?
Their periods are off.
Yeah, they have different period. One of them looks like about maybe 7.54 seconds to complete a full cycle. The other takes more than that, what's the time on it? I guess a little more than 8 seconds to complete a full cycle. So these are going to have different periods, different frequencies. They'll also have different wavelengths, but since this is a time versus displacement graph, we don't really care about wavelength. The idea is let's say these are sound waves. If you're just listening to both of these sound waves at the same location, one of the sound waves is making your eardrum oscillate with a frequency of 0.13 cycles per second. The other wavelength is trying to make your eardrum oscillate with a frequency of 0.12 cycles per second. So different frequencies. And if we wanted to figure out what kind of interference these produce, like let's say at the very beginning, time 0, these waves look like they're exactly synchronized. They're both at equilibrium on the way up. They both reach a crest at almost the same time. What kind of interference would you call that?
Constructive.
Yeah, at the beginning, they're syncing up perfectly. That's definitely constructive interference. Let me zoom out a bit, because as we go further on in time, further down the line, later on in time, it looks like we get, it might help if I relabel, I don't know if we can relabel these. With different colors. I think that might make it easier to see. There we go. Okay, so at the beginning, they're perfectly synchronized. We get constructive interference. Later on, though, what do you notice about, let's say, at this point in time? What's going on with the two waves there? If you've got a crest and a trough occurring at almost the same time.
Deconstructive interference.
Yeah, we've got destructive interference there because the crest and trough, when we add them together, will mostly cancel out. And if we go even further down the line, as we continue, again, because they're different frequencies, it looks like we get back to crest and crest lining up again, trough and trough mostly lining up. So at that time, we've got back to constructive interference. So as time passes, because these are not perfectly synchronized frequencies, the slightly different frequencies mean that each one takes a different amount of time to complete a full cycle. So as time passes, we gradually shift from constructive to destructive. And then further on, we get eventually back to synchronized, constructive again. And we just keep oscillating or alternating between constructive and destructive interference. So this tends to happen if you're looking at a time versus displacement graph of any two waves that are different frequencies, especially if they're almost, it's most obvious if they're almost the same frequency, but not quite, like 0.13 cycles per second versus 0.12 cycles per second. Very close to the same frequency, but just different enough that we're changing what type of interference happens as time passes. And we can actually see this in much more detail if we take a look at their sum. Right now, I'm just graphing both of these waves individually, but if we graph the sum of those waves, the superposition of adding the y values together, we end up with very large oscillations where it's constructive, and then getting weaker and weaker and becoming very small or no oscillations when it's destructive. It mostly cancels out. And then getting larger and larger and getting large oscillations when it's constructive, and then going back down to smaller oscillations when it's destructive. So this is what we call the carrier wave, the actual superposition, the sum of the waves showing the actual displacement as time passes. That's called the carrier wave. Any questions on the terminology there so far, or why the wave looks the way it does? So going from constructive to destructive, and then eventually back to constructive again in these repeating cycles. Yeah, the carrier wave is just the result here. When we add, so we've got the two different waves with slightly different frequencies. When we add their y values together, and that's literally all this graphing program is doing here, is just adding the y value of one of the waves plus the y value of the other wave. Because y value represents displacement, like how far the sound wave pushes your eardrum out of equilibrium. If you've got two waves in the same position, they're both trying to push your eardrum in different ways. So the summation of those, the sum of how both waves are trying to push your eardrum, tells you how far your eardrum actually gets pushed out of alignment. And so, like at time 0, your eardrum is wobbling back and forth with very large amplitude. It's wobbling quite a lot. Later on, in this case, at time 50 seconds, it's hardly wiggling at all. So you're going to hear almost no sound. It'll sound very quiet. And then at about 100 seconds, there's a large oscillation. So you're going to hear a very loud sound. And then later on at 150 seconds, very quiet sound. So it looks like this is alternating every 50 seconds, loud, quiet, loud, quiet, loud, quiet. And that's the phenomenon that we call beats. The actual graph here, the graph of oscillating up and down or back and forth or whatever, but changing amplitude, that new wave, the sum of the waves with changing amplitude as time passes, is called the carrier wave. But the fact that it's alternating between loud and quiet as time passes is a phenomenon we call beats. The beats means the alternating loud and quiet pattern. And that alternating loud and quiet pattern can be sort of summarized as what we call it's usually called a wave envelope function. The wave envelope just means some new curves that sort of surround that wave. So graphically, that's going to look like, if I just sort of trace out, let's say, the high points here and the low points. And likewise, these high points and low points. I sort of get another much broader sine wave that's called the wave envelope function. It's a pair of curves of upper bound and lower bound that describe that changing amplitude that surround the wave here. So that would be called the wave envelope. And I think the wave envelope can make it a lot easier to see the idea that we're changing from large amplitude, constructive, to small or even zero amplitude, destructive, then larger amplitude, so that's constructive, and then cycling back to destructive again. So that wave envelope shows the beat pattern, the alternating cycle between loud and quiet as we switch from constructive to destructive to constructive again, and so on. Any questions on that so far? And in this case, how much time does it take to go from loud to the next loud? How long is that cycle?
$160 seconds.
100, sorry, what was that?
160 seconds.
I think I'd call it just 100 seconds, because if you take a look at the exact pattern here, we've got this largest amplitude right here at 0. And then it looks like it gets to exactly 0 amplitude at 50. So that's the halfway mark. And I think I may have fudged the size of the carrier wave here, or the wave envelope. But I think the 100 is where it hits the next loud spot. In fact, I think this might be easier to see if we zoom out a little bit. If we zoom out a bit, yeah, notice that we're going from loud at 0 to quiet at 50 to loud around 100, and then quiet, like a dead quiet again at 150. So it looks like every 50 seconds, we're swapping from loud to quiet to loud to quiet to loud. So the amount of time from quiet to quiet, that's 100 seconds. Or from loud to loud, 100 to 200, that's also 100 seconds. So it looks like it takes 100 seconds to complete one full cycle of this, to go from loud to loud, or from quiet to quiet, constructed to the next constructed, or from destructive to the next deconstructive. And what do we call that amount of time? The amount of time for one full cycle of loud to quiet to loud to happen.
Is it the period of the beat?
Yeah, this is the period of the beat, or the beat period. Usually written as T sub beat. Because the beats themselves form an alternating cycle. It's not really it's not the period of the wave itself. The carrier wave here is oscillating much faster than once every 100 seconds. So the carrier wave has its own frequency, which is a much higher frequency, much shorter period. If you take a look at just from crest to crest of the carrier wave, this from crest, the time from actual crest to actual crest, or from actual trough to actual trough, that would be called the carrier period. And that's a much shorter span of time. Kind of difficult to tell from this graph, but we could probably count up how many cycles occur in, let's say, the first 50 seconds. So within the first 50 seconds, it looks like we've got 1, 2, 3, 4, 5, 6, maybe 6.5. Yeah, it looks like about 6.5 cycles in the first 50 seconds. So just to approximate, we could say 6.5 cycles, that is 6.5 times the carrier period, equals 50 seconds. And then we could divide both sides by 60 or 6.5. 50 seconds over 6.5 cycles in those 50 seconds. And what's that going to be? 50 over 6.5. 50 over 6.5 is about 7.7. So that means the carrier period is about 7.7 seconds. And this is just an estimate. I'm just counting about how many cycles happen in those first 50 seconds, because that seems like an easy amount of time to deal with. And then taking that 50 seconds divided by the number of cycles, and I get the number of seconds per cycle. So we'd say the carrier period is about 7.7 seconds, whereas the beat period is the amount of time span from loud to loud or from quiet to quiet. And that ties into the wave envelope we were looking at earlier. That if you trace out the outline of the wave, so something like this. And then continuing through there. So that's our wave envelope. And note that we're going from quiet to quiet over the span of 100 seconds, or from loud to loud over the span of 100 seconds. So we'd say the beat period is 100 seconds. Whereas the carrier period, the actual amount of time from crest to crest or trough to trough is about 7.7 seconds. Any questions on that terminology or those values so far? And I think it's going to be easier to see what's going on if we look at these in terms of frequency instead. If you know the period, how would you turn that into a frequency?
One over.
Yeah, we can just invert that, 1 over the period. So 1 over 100 would be 0.01 seconds. So the beat frequency, how many beats per second would be 0.01, or not seconds, hertz. 0.01 hertz, that is 0.01 cycles per second. So that means you would hear 1/100th of a beat per second. What that means is this sound is going to be alternating between loud and quiet and loud and quiet. Sort of just a wobbling sound. But it's wobbling very slowly, only 1 cycle every 100 seconds from loud to quiet to loud. So the beat frequency tells you how many of those loud to quiet to loud cycles you hear per second. Smaller than 1 means less than 1 cycle per second, only 1 cycle per 100 seconds in this case. Whereas the carrier frequency, if we take 7.7 seconds and invert that, 1 over 7.7, I'm getting about 0.13. And what would that tell us? What does the carrier frequency tell us? If we're talking about how many actual oscillations there are per second, that is how many times your eardrum actually wiggles per second. What does that tell you about the sound? How in terms of what you actually experience? Yeah, that's the frequency you hear. That's the actual note or tone or pitch that you experience. So the carrier frequency is the note you actually hear. In terms of actual experience, the note or tone that you actually hear. So you would say, I'm hearing a tone, that should be hertz, not seconds. And of course, 0.13 hertz is way too low of a frequency for the human ear to actually hear. I'm pretty sure. But this would be the frequency of that sound. Whereas the beat frequency isn't the sound you actually hear. The beat frequency is how many times that sound oscillates. Number of beats per second. So the carrier frequency tells you the actual frequency of the resulting sound you hear. The beat frequency tells you the number of beats per second. That is the number of loud to quiet to loud alternations per second. And how does that relate to the 2 frequencies of the actual waves themselves? We had one wave with frequency 0.13 hertz and one wave with frequency 0.12 hertz. How does that relate to the beat frequency? how does 0.01 hertz relate to 0.13 hertz and 0.12 hertz? Or what calculation could you do to 0.13 and 0.12 to get a result of 0.01? Can you think of any arithmetic you could do with these two numbers, 0.13 and 0.12, to get 0.01 as the result? Yeah, that's literally just the difference between them from subtracting these. So the beat frequency, and it turns out this is always the case, the beat frequency is always going to be the difference between the two frequencies. Beat frequency is difference between the two frequencies. And for the carrier frequency, cycles per second, do you mean for the beats or for the carrier wave?
For the carrier.
For the carrier wave?
Yeah.
Yeah, in that case, if you can clearly see the beginning and end of a cycle, like for instance, you could say we're going from, let's say, from this crest to the very next crest. If you have a detailed enough graph that you can measure the amount of time from crest to the next crest, that amount of time is the carrier period. And then the inverse of that will be the carrier frequency. In this case, though, the crests are so close together based on the labeling on the graph that that's difficult to tell. So what I did here was I said, well, from 0 to 50 is a pretty well-established amount of time. So I just counted up how many full cycles are there from 0 to 50. And a full cycle in this case would be from equilibrium to a crest, to equilibrium to a trough, to equilibrium again. That's one full cycle, two full cycles, 3, 4, 5, 6, and a little bit. So I was rounding that off to about 6.5 seconds, or 6.5 cycles. And the period is seconds per cycle. So I took 50 seconds, which is the amount of time that I chose to use, divided by about 6.5, because it looked like those 50 seconds represented about 6.5 cycles. And the period literally is just number of seconds divided by number of cycles. That turns out to about 7.7 seconds per cycle. Or if you invert that, you get the frequency, cycles per second instead of seconds per cycle.
Oh, okay. And then, so for the beat period, then that's from one like constructive interference to the next constructive or destructive to destructive? Exactly.
So in terms of sound, we could describe that as from loud to loud or from quiet to quiet.
Okay, thank you.
And I think it's on the graph, it can be easier to see that if you actually draw in the wave envelope, sort of enclosing the wave or enclosing the carrier wave to show just like the largest amplitude, smallest amplitude as it goes on. So we've got the beat frequency, and mathematically the beat frequency always turns out to just be the difference of the two given frequencies. So in this case, if you call these F1 and F2, the beat frequency is going to be just F1 minus F2, which we usually write in absolute value to denote that it doesn't matter what order we subtract, we always want a positive value. But conceptually, it's just going to be the difference of the two frequencies. And the 0.13 hertz I was rounding off here. Realistically, I should actually say, I'm going to say this should actually be 0.125 hertz. Because how do we actually calculate the carrier frequency from the two original frequencies? Have you seen how that's related to frequency 1 or frequency 2? How does 0.125 relate to the originals 0.13 and 0.12? Yeah, it's the average. It's exactly halfway between. So F carrier is the average of the two frequencies. So that's typically how you'd calculate it, or how you'd relate it to the two other frequencies. You've got two frequencies of the original waves that are coming in. If you take the average of those two frequencies, you get the note you actually hear, the carrier frequency. If you take the difference of the two frequencies, you get the beat frequency, how many beat cycles there are per second. Any questions on that so far? So let's see what's going to happen if you change these around. Like, let's say we take the same setup, but we make the frequencies, let's say instead of 0.13 and 0.12, let's make the frequencies a little further apart. Let's say we make it 0.16 and 0.12 instead. If I make that change, if I change the first wave to have 0.16 instead of 0.13, making the frequencies more different, what's going to happen to the beat frequency? Yeah, if we make the frequencies more different, the beat frequency is going to increase because the beat frequency is describing how different they are. So let's try that and see what happens. If I make one of these, and again, remember, these are just waves like this. We've got these two different waves like so. If I just make that one change, if I change this to, let's say 0.16, then we end up with this as our new carrier wave. So let's compare that. If I undo that change, going back to 0.13. And let me put some markers here for where it's constructive. We've got constructive interference here, and again at 100. So it takes 100 seconds to complete one full loud to quiet to loud beat cycle. But changing this to 0.16. Now we have a much faster beat cycle. Instead of taking 100 cycles to go from loud to quiet to loud, it looks like it now only takes about 25 seconds to go from loud to quiet to loud. Oh, let me make that more clear if I hide the original wave. There we go. So that's the new carrier wave, loud to quiet to loud in only 25 seconds. Because what's the difference between these two frequencies? The difference between 0.16 and 0.12 is what?
.04.
Right. The new beat frequency is 0.04 hertz. And then if we invert that, the new beat period would be the inverse of this, 1 over 0.04, which is 25 seconds. So that means it now takes 25 seconds to have one beat happen. So by making these more different in frequency, more out of tune with each other, if these are musical instruments, if we make these more out of tune, the beats get closer together in time. Whereas if we make them more in tune with each other, if we make the frequencies closer to each other, that would decrease the beat frequency. The beats would get more spread out in time. There would be fewer beats per second. But notice that the carrier frequency is still just going to be the average of these. In this case, halfway between 0.12 and 0.16 would be 0.14. So by modifying these, making them more different from each other, the carrier frequency doesn't change very much, but the beat frequency changes pretty drastically. And you can actually use this idea to tune musical instruments. If you play two musical instruments trying to play the same note, but a little bit out of tune with each other, it sounds awful. Out of tune instruments sound awful because you're hearing beats. It's not a steady tone. You end up hearing this alternating, wobbling, loud, quiet, loud, quiet, loud, quiet, and it sounds terrible. But that tells you need to tune them. If you try to tune, like let's say you'll keep one of them the same, but tune the other one, but maybe you're tuning in the wrong direction and you get more out of tune. How would you know from listening to it that it's gotten more out of tune?
If it gets softer in volume?
Well, the fact that it's out of tune in the first place tells you it's going to be alternating quiet, loud, quiet, loud. How would you tell that it's getting more out of tune versus less out of tune? If the frequencies become more different from each other, what happens to the beats? Yeah, the beats are going to get closer together. Because if the frequencies are more different from each other, that increases the beat frequency, which decreases the beat period. You get beats closer and closer together in time. So the beats are going to be coming in faster and faster, closer together in time. And that tells you you're tuning the wrong direction. You should tune it in the other way. Like, let's say you were pushing one of the mouthpieces in, or maybe tightening one of the strings. And that, if that makes the beats happen more close together in time, that means you're going the wrong way. You should loosen the string instead. So if you're turning it in the right direction, if they're getting closer to in tune with each other, the difference shrinks. So you get a lower and lower beat frequency, fewer beats per second. So if you're going in the right direction, the beats should be more spread out in time. In fact, if you get them so close together that they're almost the same, like let's say these are so close that they're like, let's say 0.12 and 0.1201. What would that tell you about the beat frequency if they're almost the same frequency already? Like if I were to keep this at 0.12, but change this one to 0.1201. If they're almost the same frequency, what does that tell you about the beat frequency? Yeah, it's going to be very, very small, which means there's very, very few beats per second. The beat period will be much longer. It'll take much more time to complete a full cycle. So let's see what that looks like. If we're just graphing the new carrier wave, notice that this looks like it doesn't even look like it's wobbling at all. I think we'll have to zoom out to see any wobble. If we go way further out in time, this does look like its amplitude is getting a little bit smaller, but we have to get all the way out to about 5,000 before it drops to nothing. And then it's going to increase again. In fact, it looks like the new beat period is 10,000 seconds. That's a very long time. So if you've got the two frequencies almost the same, if they're just a little teeny tiny bit out of tune, then the beat period is such a long time, your ears don't even notice it. And it just sounds like they're in tune with each other. So once the two frequencies are close enough, you don't even notice beats anymore. They may as well be completely in tune. In fact, if they're exactly in tune, the beat frequency would be 0, no beats at all. So this is really one of the main uses of beats. Beats can be used to determine, are these musical instruments really in tune with each other or not? And are we doing the right thing to make them more in tune with each other, or are we going in the wrong direction without even needing an electronic tuner? Any other questions on that? All right, then that's it for today. I will see you next time.
Thank you.
You're welcome.